Imagine holding an ordinary piece of rock taken from deep underground. It looks unremarkable, no different from countless other minerals extracted from the earth. And yet, hidden within that rock is the potential to power entire cities for years without burning a single gram of fossil fuel. How does that transformation happen? How does a mineral buried in the ground become precisely engineered nuclear fuel capable of operating safely inside a reactor core? The production of nuclear fuel is one of the most tightly controlled and technologically advanced industrial processes in the world. It involves mining, chemical processing, isotopic separation, ceramic engineering, metallurgy, and long-term safety planning. Every stage must meet strict physical and regulatory standards, because the final product will operate under extreme temperature, pressure, and radiation conditions. If you like similar educational content, please like, subscribe, and share the video with your friends. The process begins with uranium ore mining. Uranium occurs naturally in low concentrations, often less than a few % of the rock mass. Large quantities of ore must therefore be extracted and processed to obtain usable uranium compounds. The ore is crushed and milled into fine particles, then treated chemically to separate uranium from surrounding material. The result of this stage is a concentrated uranium oxide powder commonly called yellowcake. Chemically, it is mostly uranium oxide, and while it contains significant uranium content, it is still far from being reactor-ready fuel. Natural uranium consists mostly of uranium-238, while only about 0.7% is uranium-235, the isotope capable of sustaining a controlled nuclear chain reaction. For most commercial power reactors, this percentage must be increased to around 3 to 5%. That means the next crucial step is enrichment. Once yellowcake has been produced, the next stage is uranium enrichment, one of the most technically demanding steps in the entire nuclear fuel cycle. The challenge arises from a simple fact. Uranium-235 and uranium-238 behave almost identically in chemical reactions. They cannot be separated using ordinary chemistry because the difference between them lies only in the mass of the atomic nucleus. In natural uranium, uranium-235 makes up less than 1% of the total. Most commercial nuclear power reactors require fuel enriched to roughly 3 to 5% uranium-235. This increase may seem small, but achieving it requires sophisticated physical processes. Before enrichment can begin, uranium oxide must be converted into a gaseous compound. This is done by chemically transforming it into uranium hexafluoride. Uranium hexafluoride has a useful property. At relatively moderate temperatures, it becomes a gas. In gaseous form, its molecules can be separated based on their slight mass differences. Modern enrichment facilities use gas centrifuges. A centrifuge is a tall, rapidly spinning cylinder. When uranium hexafluoride gas is introduced into the rotating chamber, centrifugal force pushes heavier molecules slightly outward toward the wall, while lighter molecules remain closer to the center. Molecules containing uranium-238 are slightly heavier than those containing uranium-235, and over time, this tiny mass difference becomes exploitable. The separation achieved in a single centrifuge is extremely small. To reach the desired enrichment level, thousands of centrifuges are connected in cascades. Each stage increases the concentration slightly, and over many stages the final enrichment target is achieved. The enriched uranium hexafluoride is then converted back into solid uranium oxide. At this stage, it is no longer just raw material. It has the precise isotopic composition required for nuclear fuel fabrication. It is important to emphasize that enrichment levels for civilian nuclear power are strictly regulated and monitored internationally. Fuel for energy production is enriched to relatively low levels compared to other possible applications, and the entire process operates under oversight agreements. With enriched uranium oxide prepared, the next step is transforming this fine powder into dense, precisely engineered ceramic fuel pellets capable of surviving years inside a nuclear reactor. Once the enriched uranium oxide has been produced, the process shifts from isotope physics to precision materials engineering. At this stage, the uranium exists as a fine, dark ceramic powder. It may look ordinary, but its physical properties must be carefully controlled before it can function safely inside a reactor. The powder is first blended and conditioned to ensure uniform grain size, moisture content, and chemical purity. Even microscopic variations could influence how the material behaves under intense heat and radiation. The goal is to create a homogeneous mixture that will form pellets with consistent density and structural integrity. The next step is pressing. The powder is loaded into hardened steel dies and compressed under very high pressure into small cylindrical shapes known as green pellets. These pellets are typically about 1 centimeter in diameter and height. At this point, they are still fragile and porous, not yet strong enough for reactor conditions. To achieve the necessary mechanical strength and density, the pellets undergo a process called sintering. They are heated in specialized furnaces to temperatures above 1700 degrees Celsius in a carefully controlled atmosphere. During sintering, the microscopic particles fuse together, reducing porosity and forming a dense ceramic structure. The pellets shrink slightly during this stage, so the entire process must be precisely calculated to ensure final dimensions fall within strict tolerances. After cooling, each pellet is inspected. Measurements verify diameter, height, density, and microstructure. Advanced analytical techniques confirm chemical composition and structural consistency. Quality control is critical because these pellets must endure temperatures of hundreds of degrees Celsius and intense neutron bombardment for several years. Once approved, the pellets are stacked inside long metal tubes made from zirconium-based alloys. Zirconium is chosen because it is highly resistant to corrosion at high temperatures and absorbs very few neutrons, allowing the nuclear reaction to proceed efficiently. The tubes are sealed using precision welding techniques, forming fuel rods. Dozens or even hundreds of fuel rods are then assembled into a fuel assembly. This structured bundle is what is ultimately inserted into the reactor core. Once the fuel assemblies are placed inside the reactor core, the carefully engineered material begins performing its purpose, sustaining a controlled nuclear chain reaction. When a neutron strikes a uranium-235 nucleus, the nucleus splits into 2 smaller nuclei, releases additional neutrons, and produces a large amount of energy in the form of heat. That heat is transferred to a coolant, typically water, which then generates steam to drive turbines and produce electricity. The reaction is not explosive. It is carefully regulated. Control rods made of neutron-absorbing materials are inserted or withdrawn to manage the number of free neutrons in the core. In addition, the physical properties of the fuel and coolant create natural feedback effects. As temperature rises, certain conditions reduce the reaction rate, helping stabilize the system. This built-in physics is a crucial safety feature. A fuel assembly typically remains in the reactor for about 3 to 5 years. During this time, the concentration of uranium-235 gradually decreases as fission occurs. At the same time, new elements form as byproducts of the reaction. Eventually, the fuel is considered spent, not because it has no energy left, but because its composition no longer allows efficient reactor operation. When removed from the reactor, spent fuel is still highly radioactive and continues to produce residual heat. It is first placed in deep water pools located at the plant site. The water provides cooling and radiation shielding. After several years, once heat generation and radiation levels decline, the fuel may be transferred to dry storage casks made of thick steel and concrete. Long-term management of spent fuel is one of the most discussed aspects of nuclear energy. Some countries pursue reprocessing, in which usable uranium and plutonium are chemically separated and recycled into new fuel. This approach can extend fuel resources and reduce the volume of high-level waste. Other countries focus on long-term geological disposal, placing spent fuel in stable underground repositories designed to isolate it for thousands of years. From mining uranium ore to enrichment, pellet fabrication, reactor operation, and eventual storage or reprocessing, nuclear fuel production is not a single step, but an integrated cycle. It combines nuclear physics, chemical engineering, materials science, and strict regulatory oversight. What begins as an ordinary rock deep underground ultimately becomes one of the most energy-dense fuel sources humanity has ever harnessed. A small ceramic pellet can contain as much usable energy as several tons of fossil fuel, yet operate within a highly controlled system designed for long-term stability and safety.